One of the more common arguments in the Artemis space is which is the best staging orbit. And I'm here to say that you're all wrong. Everybody watching this video is wrong about the trade. A thing to emphasize at the start is that a small change between Apollo and Artemis that I don't think people have fully realized is that the landers are going to be reusable. Sounds weird to say, of course, but this is really important and has non-intuitive consequences. Also, here are my thoughts on each lander concisely summarized. Now to the logical focal point of every architecture discussion, Delta V. There are a lot of cislunar Delta V charts floating around. I like this one from NASA, although it has some issues. From the perspective of sharing Delta V between the capsule and the lander, it's better for them to be closer to each other, because wet mass increases exponentially with Delta V. Because the lander has to travel further than the capsule, minimizing its Delta V is desirable. So, staging a low lunar orbit should decrease the overall launch mass required for a mission, right? Except, there's a very subtle thing, and that is that the tanker used to refuel the reusable lander also has to travel further. The tanker ends up being roughly the same wet mass regardless of the architecture. You don't end up saving up on launches. So, you're just exchanging lander mass for capsule mass. This could be useful in the context of giving the human lander additional margins, but not a smoking gun. For certain landers, this doesn't even matter because of its inherent overshoot of the requirements. What about the other parameters of the orbits? Thermally, low lunar orbit can be really harsh. At maximum, the thermal flux can go up to 1,335 watts per square meter. For context, the thermal flux from the Sun at Earth's distance is 1,361 watts per square meter. It's like having another sun in the sky for a period of the orbit. For cryogenic stages trying to manage boil off, that's not good. In addition, it's in a dynamic, separate direction relative to the sun. Simple passive sun shields perform much worse. In regards to aborting, that does favor low lunar orbit with the ability to go to a capsule every orbit. However, recently there's been discussion that aborting to NRHO is limited to once every orbit, or 6.5 days. This isn't accurate as you don't need to wait until the optimal transfer window. You can just take a different trajectory to reach another point in the low energy environment, that is NRHO. So the abort times to reach a point in NRHO from the lunar surface ranges from about 0.5 to 2.5 days. However, the abort window to return to Earth itself only opens up once in orbit, so every 6.5 days. This means that the actual abort time ranges from about 7 to 15 days. But that's not to say Apollo lunar orbit doesn't have its own issues. The orbit's ascending node changes as the moon orbits. At its max of 90 degrees, it requires a 550 meter a second 3-burn nodal plane change to get to an orbit allowing for return to Earth. Return time to Earth at a guess ranges from 5 to 6 days. Both low lunar orbit and NRHO experience moon eclipses. However, the NRHO NASA selected was designed around avoiding Earth eclipses longer than 90 minutes. Low lunar orbit can experience eclipses of up to 4 hours. These eclipses place restrictions on the possible vehicle designs. Gateway, for instance, wouldn't work due to thermal shock of the solar panels. There are also additional things like station keeping and comms that favor NRHO, but those are more minor. Let me summarize this concisely from the perspective of the selected landers. For Blue Moon, the initial mass in LEO is the same because the tanker has to travel further. The lander itself could maybe shed 4 tons of tankage, which I'm not going to say is nothing, but it's a minor reduction given the lack of removal of complexity. From a storage orbits perspective, NRHO is clearly better. The abort setup does favor low lunar orbit, but I think that is marginal. For Starship HLS, the initial mass in LEO is a bit less because the tanker can theoretically use its heat shield to get back to Earth, so the propulsive gap to the lander is smaller. But Starship HLS will remain the same size because the size is driven by the initial architecture and Starship heritage, not reuse operations. The storage and abort situation remains the same as with Blue Moon. Then, when you factor in the crew vehicles to access the landers, which are definitively negatively impacted by low lunar orbit, I think NRHO becomes clearly better. The initial mass in LEO advantage for Starship disappears when using something like Starship Crew to transport crew to lunar orbit. If you think Orion/SLS bad and you want it to be replaced, fine. Then it's in your best interest to minimize the requirements of any replacements, and NRHO staging does that.